All right, so as you can see on the screen, this is the final lesson in terms of covering new material. I was hoping to get center of mass covered before the break, but we just ran out of time. So that's part of what we're going to do today. And then we're going to wrap up simple harmonic motion primarily by looking at pendulums. We're going to look at pendulums in a couple of ways. It comes in chapter 9, thinking about momentum and energy. And then we're going to look at it again in chapter 12 of our textbook, where it talks more about the period of time it takes to swing back and forth as a pendulum, which relates a lot to uniform circular motion. So a lot of overlapping today, a lot of things that are going to be, oh, yeah, we kind of already learned that, but now seeing it in a different light, seeing it with a different connection. So that's what's in store today. I don't know that we'll have a chance to go to the torque problem. We looked at it before break, and some of you kind of started figuring it out. It was the one where we had that crate hanging on a beam from a wall. So we may have a chance to look at that a little bit more today. We'll see if we have time or not. I doubt if we'll get to worksheet 6. We'll probably just practice a couple of those problems Thursday as kind of a quick warm up. And then we'll move on with mostly FRQ practice on Thursday, and Wednesday, it'll be only FRQ practice because we have a shortened period. So Wednesday, we're going to practice FRQs. Thursday will be mostly FRQ practice and just reviewing a variety of things, showing you some things on the AP Classroom site you could be doing on your own to prep both for our in-class exam and for the one on May 5th. But the schedule looks like this. Tonight, you have your Positive Physics Unit 14 work that is due. It is the work section, so make sure there are a lot of questions, but you can correct them as you go. You don't have to finalize it. And so hopefully you've been plugging away at that. That was the only assignment I really gave you before break. And then over break, you had the option as to whether you wanted to work on it more then or not, but that's due tonight. And if you do the corrections as you go, then you should get 100%. Then on Thursday, that's when the Unit 17 on simple harmonic motion work is due. Same kind of deal, the work section, correct it as you go. So if you get them all done, you get them all corrected, you should be able to get 100% on both. The 17 unit is much shorter. So if you haven't started it yet, you don't have to panic. It's not nearly as long as Unit 14. And you should already have done the spring Hooke's Law part. So you should already have some of it done. You just have to finish up the other parts. So that's what you have. And then next week, by next week, you need to get your Unit 23 done, which is 30 questions, which is going to serve as a test grade over all kinds of things. You know, one question on simple harmonic motion, one question on energy, one question on gravity, one question on this and that. And so it's a variety of different topics over all year. And that one is the assessment. So make sure you read the directions on the description carefully. That when you are doing the assessment, you will need to then finalize it and then do corrections afterwards. Your grade will be the average between the original and corrected score. So that's kind of how it will be curved. And that will be your test grade for basically this term. So that's what you have coming up. Those are your final assignments. After that, the only graded work in class will be the exam we take. And we'll start with the FRQs, not this Thursday, but next Thursday. So next week, we'll be taking our FRQs in class, 4 of them. And then the Monday after that, you'll be taking the multiple choice portion. And then the periods after that, we'll just be reviewing up until May 5th. After May 5th, you're no longer required to come to class, actually, because of the way the year has gone with being in and out, and because so many students are still hybrid. The administration said for our AP classes, once we're done with the exam, class is optional. Now, some teachers have other material they need to cover for a variety of reasons. Some have their exam later. Some are having a separate exam, but we're going to be done with our exam before you actually take the College Board test. So there's nothing for us to prepare for afterwards. So classes after that, May 5th, will just be optional. And if you are studying from home, you can just let me know, hey, Mr. Webb, I'm working on some makeup work, or I will have some optional assignments for you if you need to improve your grade in some area. And so you can just email me or message me through Access and say, hey, Mr. Webb, I know we don't have a formal class today, but can you help me with this question? I'm trying to do this makeup work. I'm trying to do this extra work to boost my grade. And I'll just turn on the Zoom and meet with you, kind of have office hours. So basically I'll be here and I'll be in the room. So if you're bored and you want to come in and do a physics lab, come in and do a physics lab with me. If you just need a quiet place to study and you like for other exam, come in and hang out. If you just need to blow off some steam, you know, come in and I'll have a couple board games or something later and play a board game with me. So, you know, just I'll be here and I'll be available. The only class I'll be teaching is the electrical engineering class at that point. So if you need help with anything, if you're trying to make up work, if you're trying to improve your grades, that'd be a great time to get that kind of more individualized help. Or like I said, if you just need a place to hang out, you know, you're welcome to come by anytime. And I'll remind you of all those details later, but that'll be give you the opportunity that if you need to, then to focus on some of your other classes and really give them the attention that they may need as their exams and so forth come to the surface. So any questions about the schedule, what's ahead? I don't think so. Obviously, you can always look at the Axis calendar to see when everything's due. So all of these due dates and descriptions are on Axis calendar. I also, on the bulletin board of Axis, put the calendar of what days we're reviewing and what days we're taking the exam in class, so you can look at that as well. But that's what we have on tap. And if there aren't any questions, let's go ahead and jump into the final lesson. All right, so center of mass. I'm going to move this over here. Oh, Kyle, you got your camera working. Good to see you. So the center of mass is something that probably all of you have some intuition about. It's not a very complex concept, but we're going to learn how you can actually mathematically determine where it is, which I would say there's a 95% chance you won't have to do. But just in case, I want to at least look at it one time in case it shows up. But you will for sure need to understand the meaning of it and understand a couple of kind of unique scenarios that may not be completely intuitive. And you may also need to describe how you could determine the center of mass in an experiment. Because on the FRQs, if you're taking the May 5th version with 5 FRQs, one of those FRQs will be experiment-based. And if you're taking the one on June 9th that's online, it may or may not be. There's only 2 of them, and they may or may not be. It hasn't been clarified whether they will be experiment-based or not. I think they could be, but they don't have to be. But in the 5, there will be one for sure that's focused on lab. And one thing you might have to do is explain how you would determine the center of mass for an object. So I'm going to show you that in our notes today. So the center of mass is the point that exists in an object, or sometimes it's not even within the object. It can't actually be outside the object, but it's the point through which all of the system's mass, if all the system's mass was concentrated there, that's the point that would actually move through a parabola, for instance, if it was a projectile. So if I tossed this ball, for instance, we know from first semester, it would be a projectile. It would travel along that parabolic path. But not every point of the ball travels along that parabolic path, because if I throw a ball, most likely it's going to be rotating as well. And so as it's flying through the air and rotating, some points on that ball will be not exactly following that parabolic path. They'll be spinning. But there will be one point, that center of mass, that is following the projectile path, that is following that parabolic path. And we call that point the center of mass. Now, for objects like a ball, like a sphere, it's just the geometric center. Pretty easy. And so when you're drawing a free body diagram, we've actually done that a lot. We've had normally shaped and irregularly shaped objects, and we've just kind of, it's like roughly here, you know, and we just make a dot and we just draw, right? Well, today we're going to talk about how could you actually figure out where it is. Because if the object is flying through the air but does not have a regular shape, like this crazy, whatever it is, some weird looking tomahawk thing, I don't know. If this is flying through the air and rotating, same as the sphere, there is a point somewhere in that object that would be called the center of mass, and it would be following that parabolic path, but all the other points would have angular acceleration, and they wouldn't necessarily be exactly following that path. It would just be the center of mass. All right. So that's what we mean when we say center of mass. It is the point that follows the path of movement, whereas other points on that same object may or may not. If I don't know if you've played golf, baseball, tennis, where you have a bat, a club, a racket, and it slips out of your hand. I think I've had it happen in basically all three of those sports at some point in my life. And when the bat or the racket or the golf club flies through the air, it doesn't fly normally because, you know, like a golf club, it's got the heavy end and it just kind of looks weird as it's flying through the air. There's only one spot that actually is traveling along its normal parabolic path. The rest of it's in rotation and moving in all kinds of directions. All right. The thing that we know, though, is that because of Newton's second law, if we apply a force, there has to be an acceleration. And so if I apply a force to this weird shape, that object will accelerate. But the only point in the object that we know much about is the center of mass. The center of mass is what we know will accelerate along the direction of the net force. The other points will have additional angular accelerations that we'd have to factor in. But there is that one central point that we know will travel along the direction of the force vector. The acceleration of that center of mass will be along the line of the direction of that force. Now, if it's a simple shape, like a sphere or a disc, it's pretty easy to identify. It's going to be the geometric center. If it's any of these geometric shapes, triangles, rectangles, squares, other parallelograms of any sort, we can figure out through geometry where that center of mass is. Typically speaking, you're going to draw diagonals, you're going to draw bisectors, and where they cross, that's the center of mass. You just follow your geometric principles. There are some that are unusual, even though they are regularly shaped, though, like a hoop, where the hoop's geometric center is the center of mass, but the center of mass is not actually where there is any mass. Right? There's no mass in the center of the hoop, but that's where the center of mass is. So if this hoop is rolling down a hill or flying through an air and rotating through the air, that imaginary spot in the middle where there is no matter, at least no matter that's part of the hoop, that's the spot that would follow the parabolic path. That's the spot that would follow the direction of the force and be accelerating in that same direction as the force. So sometimes the center of mass is actually outside the object itself. Or if it's a hollow sphere, again, it would be in the middle of the sphere, but there would actually be no matter there that makes up the sphere. It'd just be air, unless it's a vacuum filled, or not vacuum filled, but a vacuum evacuated sphere. All right, so what if you have a weird shape? What if they ask you to come up with an experimental procedure to determine the center of mass, and you have some strange shape like this L shape here, where one side's skinny and one side wider, so the mass isn't evenly distributed? How can you experimentally determine it? This is something you probably won't have to do, but might. So just in case, I'd like to explain how you can do it. You take the object and just hang it from a string so that it's just letting gravity pull it down. And then you, with a ruler or tape or more string, just extend that line that the string follows through the object. So you could just take tape and run a piece of tape right along that line as if the string continued through the object. The center of mass will be on that line. Right? Now, all you have to do to find the center of mass, though, because if you have a line, we don't know where on that line it is. We know it's on the line, but we don't know where. So we have to do it again from another position on the object. So spin it and hang it again. Keep the line from the first one. So that's the line from this. That's that same line. Now we draw another extension of the string and see where they intersect. That's the center of mass. So as long as you hang the object from two different positions and extend the line of the string visually with a marker, with tape, with some other string, if you do that twice, where those two imaginary lines or tape lines or marker lines cross, that's the center of mass. And it doesn't matter how you hang it. If you hang it from a different part and extend the string, it'll go to the same position. If you hang it even from not one of the corners, just somewhere else on the object, still the string extended will go through the center of mass. So that is how you can experimentally find the center of mass for an object. And you can see for this object again, the center of mass is actually outside the matter, right? It's not part of the actual L-shaped object. It's somewhere outside of itself. But that is the only point of this object. If I threw this like a boomerang or something through the air, just that point that's actually outside of the object itself would be the only point that travels along the parabola. The rest of it would be rotating and have angular acceleration. Any questions about center of mass or how you can find it? All right, so we know a little bit kind of conceptually, experimentally, how do you find it, but what if you have to actually mathematically find the center of mass? There's a couple things to think about here. One is the idea of torque. The idea of torque can help you figure out where a center of mass is. This is something you can try at home. You can challenge if you have siblings or parents that are willing to try. You can have them see if they can stand firmly against the wall, backside and heels up against the wall, and see if they can touch their toes, and they will not be able to. It doesn't matter. Someone might think, well, I'm really flexible and I got good core strength, I can do it. They can't. It's physically impossible. It's not, it has nothing to do with how flexible or how strong you are. And if you understand physics, you can understand why. Normally, when we bend over to touch our toes, we just naturally push our backside back, and our head starts to come more over the top of our feet, right? We're trying to make our center of mass over our feet so we don't tip. If I lean back too far, I tip backwards. If I don't lean back at all, I tip forwards because my center of mass. It doesn't matter how strong or flexible I am, right? And so you can't put your heels and backside firmly against the wall and bend over and touch your toes without any extra assistance, because your center of mass is in front of your feet.
Oh, okay, I think I know what you mean.
Yeah, so in here you can see that with this picture, because her backside goes backwards, her center of mass is still above her feet, so she can keep her balance. But if her backside and heels are against the wall, there's no way to move her center of mass over her feet. It will be in front of her feet. And because it's in front of her feet, that means it's creating torque. And torque causes rotation. And there's no balancing torque to stop that rotation, right? Now, if you hold the person, you can, like, if someone stands against the wall and you hold their shoulders, you can create an opposite torque to balance them. But without that opposite torque, if they're not hanging on to anything and no one's hanging on to them, there's no opposite torque to cancel that torque, and so they will rotate.
Technically, if they had really strong ankles,
That's what I was thinking.
couldn't they push really hard down their toes and
Push.
stay in that position?
What if they're wearing
That
like
wouldn't
really
change their
heavy
center of
shoes?
mass. Their center of mass would still be out here. So there has to be a, like, this is the lever arm.
With their toes, it'd still rotate them the same way.
This is the lever arm here, this part of the body, the torso and the
Oh,
head.
yeah, you're right.
So this is the point of rotation. So we have to have some force along the lever arm, and this wouldn't be along the lever arm. So there has to be something on the torso or the head to counteract that torque of the center of mass. So just a little example, how you could kind of test this, challenge people. Here's how you can actually calculate it mathematically using not exactly the formula for torque, but the concept of torque. So in this example, we see that a person is laying on a plank that's supported on two different scales. And you can see they're not, first of all, laying in the center of the board. Secondly, our body in a typical human body is not evenly distributed. You know, the head is the heaviest part of the body. And so they've got the heaviest part of their body on the far end of the plank. And so there's going to be more weight on that scale than there will be on the other scale that's past their feet, right? So here we can see with this example, the left scale underneath the person's head is 290, and the right scale out past the feet is only 122 in terms of Newton measurements. The question says, where is the center of mass? Find the center of mass. And so there is a relationship that's similar to torque. And in fact, if you think about what we're looking at here is mass times the distance from the axis of rotation instead of force times distance. So it's not really torque. But if we turn this to weight and turn this to weight and turn this to weight, they would all just be multiplied by g, which means it would cancel, right? So you could do this with torque, but they're just showing it here with just mass instead of weight. All right. So basically here they're saying if you know the total mass times the center of mass, so this cm is not for centimeters, the cm is for center of mass, and x is for position. And this is not an equation College Board gives you, and like I said, I would say there's a 99% chance you're not going to need to do this on the exam. But just in case, I want you at least to have seen it before, and so you can kind of process it. So if we add up the total mass of the board and the person, and then we multiply it by wherever the center of mass is, that is not exactly torque, but it's relative to torque, right? It's including the mass, or not exactly weight, but, and then comparing it to the torque of the two different positions. And so then we've got the other two spots that we know some information about, these two spots, all right, added together. So those have to balance. Now, if you did it with torque instead of mass, that's fine. This just simplifies out the G's, right? So it's a little bit less to deal with. So if we think about the weight being 290 and 122, that means in total it's 412. And if we think about it as mass instead of weight, we just divide them all by G. So instead of 290, it's 29. Instead of 122, it's 12.2. Instead of 41.2, it's, or sorry, instead of 412, it's 41.2. So just changing all of those to masses. And we know the position of all of them except the center of mass position. All right, that's what we're needing to solve for. So if we plug them in, we know the 29 kilogram mass is this part, and that is 0 distance from the axis of rotation. They've just chosen this to be the axis of rotation. And then the 12.2 kilogram over here is 2.5 meters from the axis of rotation. And the total mass is 41.2 kilograms. So proportionally, we can figure out that the center of mass for this object would be 0.74 meters. So it's just a way to use somewhat the concept of torque to know that, hey, this is balanced. The person's not actually rotating, so there's a balanced torque on these 2 points. Kind of like the bridge problem, right? We try to figure out the normal force of the 2 supports on the bridge, or the truck problem, then the force of the road on the tires of that truck that we did. Similar kind of concept. We know that there's a balanced torque because the person's not actually rotating, but that doesn't mean the forces are balanced. So this is how, now, so this is kind of a shortcut. You could go through a whole torque force analysis and figure out the center of mass, but this is just showing you kind of a shortcut equation that could help you do it more quickly, more efficiently. All right. So this is an equation you may want to include in your list of equations that can be helpful, but that College Board doesn't provide. Any questions? All right, so here is a scenario and a new term, center of gravity. So we've been talking about center of mass. Now they're saying center of gravity. Well, how is mass different from when we think about gravity? If we take mass, but we also consider the effect of gravity, what are we really talking about? Force. A force, and specifically that force would be called weight, the object's weight, right? So it's almost like saying the center of weight as opposed to the center of mass. Does the mass depend on gravity?
No.
Does weight depend on gravity?
Yes.
Yes.
Yes. So the truth is, if they use the center of mass and the center of gravity for all relatively small objects close to the Earth-ish, they're the same. The center of mass and the center of gravity will be the same. Because unless it's a very massive object, the value of G is going to be constant. For a person, for instance, the value for G at the top of my head compared to my feet is virtually identical. I mean, there is such a small difference. Because if you think about it, that's based on how far I am from the center of the Earth. So like my 2 meters basically is making nothing compared to the thousands of meters for me to the center of the Earth, right? So the value of G is basically identical. It would have to be a huge object. to have any effect. Or it would have to be an object that is in space, for instance, where it's at a different distance, and now that G value won't be the same. It's still within, like in the space station, it's not going to change much within the space station, but if you're comparing one satellite to another satellite, now G is different, because they're farther apart from each other potentially. All right, but so most of the time though, center of gravity, center of mass, same thing. So here's the question though, this broom balances at its center of gravity, which would be the center of mass as well. So you could balance it and it wouldn't be in the middle, like you wouldn't balance it here. Logically, you would know you'd have to do this because you've all been on a seesaw before, right? You know that that has to be over here somewhere to make that balance. But if we cut it right there, if I cut the broom right there, would the handle have more weight or would the brush end have more weight?
Would they be the same?
Are you cutting it at the finger?
I'm cutting it where it balances.
Would they be the same?
Wait, no, they wouldn't.
They would have the same mass, but not the same.
No, they wouldn't, because
Because the
handle's way longer, so it
the
has.
short end would weigh more. Right?
So
Oh, yeah,
The
because,
broom end would weigh more,
yeah.
because the left side gets all of its torque from distance, whereas the right side gets all of its torque from force.
yeah, so the initial reaction is, oh, they're going to be the same. And then when you stop and think about it, it's not the weight that gets balanced here. It's the torque, right? It's not that the weight is balanced, it's that the torque is balanced. And so the center of mass for this handle is way over here. Just the handle, right? It's way over here. So that mass is a long distance from this axis of rotation. The center of this broom head is here, much closer to the axis of rotation. It's the torque that balances. When the torque is balanced, it doesn't rotate, right? So it's a kind of a tricky question, but it goes back to that whole seesaw idea that this heavier kid is creating the same amount of torque as this smaller child because they're at different distances from the axis of rotation. Their weights aren't the same, but they're generating the same amount of torque, right? So the broom parts aren't the same weight. They just are generating the same amount of torque. And that's where you have to switch gears a little bit. And so that's a question you could get tricked by in the multiple choice portion, for instance, where they might ask about center of gravity, center of mass. And if your assumption is their weights are balanced, you're making the wrong assumption. Think about, oh wait, the reason it doesn't rotate is because the torque is balanced, right? Not the weight. So you have to consider both the weight and the positioning of that weight. Questions about that? Little tricky thing that sometimes you see on the exam, trying to throw a lot of little examples out there for you to think through. All right. Now, this is just how you could determine it mathematically. If you know the mass, G is the same, and you know the distance, you can actually cancel out the G, right? So you really only need to know the mass and the distance, which goes back to that equation, right? They just canceled out the G and just focused on mass and distance. Because here, this is the torque of the girl equals the torque of the boy. But the G is the same for both. It's just the mass and the distances that are different. All right. Now here's one that this kind of relates to the question, Andy, I think you were thinking of with the explosion in that momentum question on positive physics. It doesn't focus on the momentum here as much, it focuses more on the center of mass. But when you have an explosion doesn't necessarily mean a bomb. Well, this is, and I think the one that you were looking at was kind of like that, right? More of a bomb type scenario. But an explosion could be a lot of things. So if you guys have ever seen these, I don't know if you can you guys on the camera see this little, it's like one of these little spring toys you might get at a McDonald's meal or something. If you've ever used one of these, you push it down, it's got a little suction cup. And so I've stored a bunch of elastic potential energy in, and eventually the suction cup gives way and that elastic potential energy gets turned into kinetic energy, right? We got a transition of energy from elastic potential to kinetic. But
That's a really good one.
Yeah, it took me, first period, I didn't pull one out ahead of time. It took me
Oh.
like 5 tries to find one that worked, because they're really old, so these
Yeah.
suction cups are all warped.
Yeah, normally the suction cups don't work, or they stick too well and they
Yeah,
never
they-
And
pop.
then they, yeah.
Yeah, yeah, 10 minutes later. But anyway, this would be an explosion. It's not a bomb, but what's happening here is you've got the foot and the chick, the bird, and they're together, and then they explode away from each other, right? The foot pushes this way, and so the bird pushes that way, but because they're connected, they both fly. All right. Another example of an explosion would be 2 people standing on roller skates with their hands together, and they push each other. And then they roll away from each other. That's an explosion. So when we use the word explosion in physics, it isn't necessarily a bomb, although it could be. But the weird thing about explosions with physics, momentum is still conserved. There's nothing weird about that. The before momentum has to equal the after momentum, and the total energy has to stay conserved. Not the kinetic, but the total. All right. But the weird thing is that the center of mass will not be necessarily in either of the objects. The center of mass will be in the center. And it depends on what kind of explosion we're talking about. So we're going to look at another example. If all of these pieces go at the same momentum values, the center of mass just stays where the bomb was originally. Now, that's a pretty unusual scenario. A more common scenario would be like 2 people on roller skates pushing each other. Because the chances of those 2 people having the exact same weight, not likely, right? Or the exact same mass. So in this case, if we have a 2 kilogram block and a 3 kilogram block, like 2 people standing on roller skates with different weights, different masses, if they're connected as a system, they're kind of holding hands. The center of the mass of the system is not in between the 2 people or between the 2 blocks. It's in the center of the whole system, right? We would have to figure out exactly using the torque relationship, where is this center of mass? But it would be closer, it would be actually within the 3 kilogram object somewhere. That makes sense? So that's the center of mass. Now, if this object is already moving and then explodes, not explodes like a bomb explodes, but explodes just as in they separate from each other. So it's moving at 4 meters per second. A trigger makes them break, and then they continue to move. Momentum is still conserved. We can still do the momentum problem like we did every other momentum problem. The momentum before, they had a total mass of 5 kilograms and a speed of 4 meters per second. So a momentum of 20 has to equal the momentum after. The 2 kilogram one is only moving 1 meter per second. The 3 kilogram one's moving 6 meters per second. 2 plus 18 still gives me the 20, right? So momentum is still conserved, but notice the center of mass now is no longer in either object. It's in the space between them. Okay, so most of the time it doesn't really matter. But there are rare occasions where they may ask a question about that, like sometimes just randomly as a part D, it'll ask, where's the center of mass? Okay. And so, like I said, I would say there's a 99% chance you're not going to be asked anything about that, but it could show up. And so I want you to have seen examples where, oh, the actual center of mass is not in the middle of either of these objects. They each have their own center of mass, but the system has a center of mass as well. And if you've never thought about a system having a center of mass, that could be pretty confusing if they say anything about it on the exam. So I just want you to have heard that idea that yes, this 3 kilogram object has its own center of mass, and this 2 kilogram object has its own center of mass, but the system as a whole still has its center of mass as well, even in an explosion. Any questions about that? The weird thing I think about center of mass is that sometimes it's outside of the object itself. And so just recognizing that and being unfazed by that when you see it can help you have confidence to answer the rest of the question. Right now let's start moving into simple harmonic motion with an explanation of pendulums. But we're going to start with energy and momentum, how it relates to pendulums, before we talk about the simple harmonic motion part. So in a ballistic pendulum, this is a common example. This problem, I would be shocked if there's not something about a ballistic pendulum somewhere on the exam. whether it's in the multiple choice or free response, I think you will likely see something about this kind of an example. It's a very, very common kind of problem. It may not be this involved. It may not be FRQs type. It may just be multiple choice type, but you still need to be able to think through the connections here. So what's going to happen is we've got this 5 kilogram block that's pulled up 1 meter on a pendulum string. And we've got this 4 kilogram block that's just hanging, not moving at all. And if we let go of that orange one, it swings down and hits the green one and sticks to it. So what kind of collision is that? Inelastic, yeah. So inelastically sticks to it. And then that means as they hit and stick, it's not just going to stop, right? It's going to hit and stick and they're going to swing up. Now, will they swing up to 1 meter on this side?
No.
No, because now it's 9 kilograms of mass. It's not going to swing up as high. It's going to swing up to some lesser height. Well, that's what if it is an FRQ kind of question where they actually want you to calculate it, that's what they would typically ask you to determine is what is the height that it swings up to after this ballistic pendulum connects and continues to swing. So my question to you, is momentum conserved?
Yes.
Yeah, in every kind of collision, right? Is kinetic energy conserved?
From the end of the collision to the height of pendulum is.
So is that the kinetic energy?
Oh, no, not kinetic.
Yeah, so that's the thing is we've just recently said, hey, for inelastic collisions, kinetic energy is not conserved. That's still true. But what Ethan said is also true. The total mechanical energy is. So that's where a lot of times students will think, oh man, it's inelastic, so there's conservation of energy doesn't apply. That's not quite right. The conservation of kinetic energy doesn't apply, but the conservation of total energy does. Okay, so what kind of energy does it have at the beginning? Just the orange block by itself. Gravitational potential. It has height, so it's going to fall, and that gravitational potential energy is going to become
Kinetic.
kinetic. It's going to move. Then when they hit, they're both going to have kinetic because they're both going to move. But then as it swings up to the peak, right at the peak, what do they have?
Gravitation.
Only gravitational potential. Right? So as this pendulum swings, at the beginning, it only has gravitational potential. At the end, it only has gravitational potential. And assuming there's no dissipated energy, those two amounts have to be the same. That make sense? So with what's given, how can we figure out what that height is? All right, well, here is the kind of sequence of steps we could go through. We don't need to think about momentum right off the bat because they're separate objects. So we would probably want to start with the whole idea of energy. This system starts only with gravitational potential energy, but it becomes kinetic. So let's look at it as kind of 3 phases. Let's look at it right up to the collision, and then during the collision, and then after. All right, so leading right up to the collision, we can focus on the energy. The energy of the system before has to be equal to the energy of the system after, if we're talking about the total mechanical. And in this case, there's no spring, so there's no elastic potential energy. It's just kinetic and gravitational. That's the only 2 kinds of energy. Well, we know the equation for both of those things. Kinetic is 1/2 mv squared. Gravitational potential is mgh. In the beginning, it did not have any kinetic energy because the orange block and the green block, neither one were moving, right? So no kinetic energy at the beginning. But the orange block had gravitational potential, a mass of 5 kilograms. That's what the mass of the orange block was. Times g, they're using 10 here, times 1 meter, how far it can fall. Now, this is another time where students kind of get confused. So wait a minute, Mr. Webb, it's not really falling 1 meter straight down, it's curving as it falls. But energy is a scalar. So does the direction even matter? We just need to know how far did it fall. That's the power of energy. It's a scalar value, so we don't have to concern ourselves with direction. All right, so we know it has that 50 joules of gravitational potential energy. Now, right as it reaches the bottom and is ready to collide with the green one, all that gravitational potential energy would have been converted to kinetic, right? it's fallen all the way down to 0 height. So now right as it's getting ready to collide, it has no gravitational potential energy. Now it's all kinetic. And so we can actually figure out, well, how fast is it going? Because afterwards, it's got only kinetic with no gravitational. We just solve for the second velocity. And if we just follow through with the algebra, we can see that that orange block started from rest, changed its gravitational potential energy to kinetic, and ended up moving 4.47 meters per second, right as it starts to collide with the green block. So we've just really analyzed the orange block in the before. Make sense? All right, so now we can do a momentum example because now there's a collision, and collisions are perfect examples of when we want to use momentum. If there's any kind of collision in the problem, chances are you want to use momentum, and you may also want to use total energy, but if there's a collision, you for sure probably want to use momentum at some point. So now they're colliding. Let's do our momentum example because even though it's inelastic, momentum's always conserved. So we can take this velocity that we just found for the orange block and recognize, okay, here's our momentum before they collide. Here's our momentum after they collide. Before they collide, the orange one had 5 kilograms of mass and it was moving 4.47 meters per second. The green one was just hanging there, so it had no momentum. It had inertia, but no momentum, right? So don't confuse inertia and momentum. Afterwards, they stick together, so now their masses are combined and their velocity is the same. So they have a single common velocity. So over here, we know that the momentum before is 22.4, and after it's got a mass of 9, so we can figure out, okay, once they collide and stick together, as a combined system, they're only moving 2.48 meters per second. That orange block is going to be slowed down in this collision. Questions? Well, now that we know how fast they're both moving, what kind of energy does that help me determine? Kinetic. And what's that kinetic energy going to become as it swings upward? Gravitational potential. And they should be equal. So we can take that velocity that they have after they collide and say, well, now it has kinetic energy because they're moving 2.48 meters per second. And they have a combined mass of 9 because they're stuck together. So now they've got a kinetic energy of 34.7, but they have no gravitational potential. When it reaches the peak, it has no kinetic because at that point at the peak, it stops moving for that instant, right? 0 velocity, 0 kinetic energy. But it's all now gravitational potential. Still a total of 9 kilograms, still has a G of 10. And now we can find the height. So this would swing up to a height of 0.309 meters. This is a great example of a problem that requires you to think about energy and momentum and even connects it to a pendulum, which is a new concept for today. Any questions about this example? If it's in an FRQ, this is how you would want to go about solving it, thinking about both the energy and the momentum transitions. Based on trends that I've seen the last few years, my assumption is you might have to do this without any numbers, just using variables,
Yeah.
which would be a
Can't
lot of
wait.
fun. And so you may have noticed that I highlighted the velocity in blue and then moved it over, and then highlighted the velocity in green and then moved it over. If you were doing all variables, that's the same process. You're finding that final velocity of the orange block and then moving it to the momentum equation. So if it was all variables, that answer becomes your V1 for the next step.
That's really unfortunate.
Yeah, so, and then your V3, when they're combined, becomes the velocity in your last step. So if you were just using variables, you would go through all the same process and you would just be plugging in the variables and solving for H. So you'd end up getting H equals 1/2 M1 plus M2 times V3. You'd have this equation basically divided by M1 plus M2 times G. So you'd have all these variables figure out what the H is. Just a prediction. I have no insider knowledge, but that's just a prediction that I could see happening. All right, so summary of chapter 9. Momentum was the key concept. Momentum is lowercase p is the variable and it's mass times velocity. And we know the units for momentum are typically kilogram meters per second, but technically you could also call it Newton seconds. And it is a vector quantity. So while energy is scalar, momentum is a vector. And so we do have to think about the direction for momentum. And it is always conserved in all kinds of collisions, elastic, inelastic, partially inelastic, it doesn't matter. Momentum is always conserved. If you don't know the mass or the velocity, but you do know the force applied and how long it was applied, you know the impulse. And the impulse momentum theorem tells us, hey, whatever that force times time is, that tells me how much the momentum will change. So you can go back and forth. You can find the impulse from the momentum, or you can find the momentum from the impulse. Very handy in solving a lot of kind of problems. And then we just finished up today with a quick understanding of what is the center of mass and how would we determine it experimentally and mathematically. So a quick overview of everything we've covered in chapter 9. All right. Let me stop that share and switch it. We're going to actually focus now on the simple harmonic motion, mostly of pendulums, but we'll touch on some other things as well. At a little review of some things while we talk about pendulums. So if you look at chapter 12, the title is Oscillations. And you can see the first area is about restoring force. We've already talked about restoring force, that springs are an example of restoring force. They try to restore the original equilibrium position. They try to, if you push on a spring, it pushes back. If you pull on a spring, it pulls back, tries to restore its natural shape. So a spring is a good example of a restoring force, but pendulums do the same thing. If I pull an object out to the side on a pendulum and I let go, it tries to restore itself back to that bottom resting position. But because it has momentum, when it reaches there, it swings past it and then it tries to restore it back this way. Both examples are what we call simple harmonic motion. Harmonic just means repeating. And there's a lot of overlaps to uniform circular motion because uniform circular motion also repeats. So we're going to see a lot of similar concepts. We've already talked about the energy of a spring system. We're going to talk about the period and energy of pendulums as well to wrap it up. So that's what we have to look forward to. We'll go through this chapter pretty quick. So some key words that you'll need to make sure you understand. I don't think either one of these words is probably outside of your current knowledge, but just in case, oscillation just means something is moving back and forth on either side of an equilibrium position. So a pendulum swinging back and forth to the left and to the right of some equilibrium position in the middle. Or a spring bouncing, an object on a spring, bouncing back and forth through an equilibrium position that's in the center. So equilibrium position is just that point in the middle. And the key thing about equilibrium in terms of problem solving is what it says here on the slide. When it's at equilibrium position for simple harmonic motion, the net force is 0. And if there's torque, the net torque is also 0. That phrase might be the most important thing to remember in this unit, that when you're at the equilibrium position, there's no net force, which tells me what? There's also no what? If there's no net force, there's no acceleration. And then there also, we know that there's no net torque at that position. All right, both of those things can be huge in terms of helping you solve problems, recognizing that there's no net force and there's no net torque. All right, so let's look at some different examples here. Let's start with some things that are somewhat familiar. So we've talked a lot about the restoring force of springs before. So if I apply a force to a spring and stretch it, it's going to pull back and then it's going to oscillate back and forth. And in the middle, there's going to be this equilibrium position, but on either side, the spring is applying a force to try to restore it to its equilibrium position. And we know that in this kind of restoring force system with a mass on a spring, again, this is something even more than a pendulum question. I would be incredibly shocked if you don't see multiple questions of a mass on a spring, both in the multiple choice and in the free response. It would just blow my mind if you didn't see it in both sections somewhere.
I thought like unit 12 wasn't gonna be on the AP test though.
Well, this is just chapter 12 from our book.
Oh.
So this is actually unit 6, I think, on the AP formula page or AP classroom page.
That makes sense.
All right, so that is something to keep in mind. We know that at that equilibrium position, the spring is not pushing or pulling, so there's no net force, therefore no acceleration. So here is just a nice sort of overlaid picture. The top showing you when it's all the way stretched to the right, there's a big force, because remember, springs provide variable force. The more you stretch it, the stronger the force. So all the way out to the right, big force, therefore large acceleration. Only a little bit to the right, less force, so less acceleration. Right at equilibrium, no force. The spring's not pushing or pulling, so no acceleration. And then it starts to compress. If it compresses a little, small force, small acceleration. If it compresses a lot, large force, large acceleration. To sort of talk through this all before, you just want to make sure that you're remembering this pattern. And we call it simple harmonic motion because this sphere, this ball, is going to oscillate back and forth, left, right, left, right, left, right, across this equilibrium position. That's what we mean when we say simple harmonic motion. Simple meaning not easy. Simple meaning it's not, it's very patterned, it's very predictable. Okay, there's nothing unusual happening here. The spring's gonna follow Hooke's law, like there's no external forces. It's just a simple example where we have none of those extra things to consider, where we would need calculus to solve it in most cases. All right, so harmonic meaning that it's rhythmic, it's patterned. All right, now a pendulum has that same idea. The pendulum is also a restoring force, pulling, and I don't know if you know this term or not for a pendulum, but there's obviously a string or a cable, and then there's the object at the bottom. The object at the bottom is called a bob, B-O-B, but it's not named after someone, so they don't capitalize. It's not like the name Bob. It's just I don't know where it came from, but that's what we call the object hanging at the bottom of a pendulum. It's lowercase b-o-b, bob. So in this pendulum, this bob is, because of its weight, pulling back to the middle to restore this pendulum back to its center position. And so as it oscillates back and forth on either side of that central equilibrium position, the torque that's created by that bob's weight pulls it back to the middle. Eventually, over time, we know because there actually is air resistance and other dissipated energies, eventually it'll just come to rest and there will be no net torque. And so there will be no angular acceleration and there will be no linear acceleration. But there will be, if it's moving at this point, let's say it's at this point, but it's moving. Okay, it's swinging. So at this point, right at this instant, we could freeze frame it, but it was in movement. No linear acceleration, because it's reached equilibrium. No angular acceleration, because this weight is not creating any torque. All right. But what kind of acceleration does it have?
Centripetal.
Centripetal, because this tension is making the bob go back to the center, right? So it still has centripetal acceleration, just not linear or angular. All right. Now, if it's just hanging there, it doesn't have any. It's just balance forces. But if it is swinging, it would still have centripetal acceleration at that point. So if we break down the idea of torque here, we know torque is a force applied along a lever arm at a distance from the axis of rotation. Well, the axis of rotation is going to be this spot right up here at the top where it connects to the ceiling. And as we look at the object out to the sides, the weight has a vector or a component that's pulling it back to equilibrium, trying to restore its position. That means that force will create torque because it is at some r distance from the axis of rotation. It's going to be at some angle, normally 90 degrees, and it is some amount of force that creates it. So when it's right here in the middle, there is no net torque because now that force is in line with the lever arm. So there's no R value or theta. I guess there is an R value, but there's no theta. All right, so if we look at the different positions, just like linear acceleration changes in a spring, the angular acceleration changes here. Down here in the bottom corner, you can see they remind you of the other torque equation. Newton's second law for torque. Torque equals I alpha. Instead of MA, it's I for rotational inertia and alpha for angular acceleration. So just like in a spring where the larger force creates a larger linear acceleration, in a pendulum, the larger torque, the farther out it is from equilibrium, the greater the angular acceleration. So it's still just following Newton's second law, but Newton's second law for torque. And just like the spring bouncing back and forth in equilibrium, no net torque, no angular acceleration. Any questions about a pendulum's restoring force, how it relates to torque, how it relates to the spring oscillation? Yeah, Ethan?
This isn't quite physicsy, but if you scaled all of those net force arrows,
Mhm.
would their tips all be along a line?
If you scaled them.
Like, so if they were
Forever.
as long as their Newton value, if they were
Oh,
all, if it was 5 Newtons, then it'd be 5 units long. Would
Uh-huh.
their tips all align in a row, like in a perfect line, or would it make like a curve?
No, it should make a perfect line.
That's pretty neat.
Yeah. And you can find it by you doing the tip to tail. So it's a little easier to see if we go back to just one, so there's not so many of them. But if we take this FG blue arrow and put it tip to tail with this FT, so we take this tail and line it with this tip, you can see how it makes the triangle.
Yeah,
So that triangle, if we go back to here, that triangle just keeps changing, right? If we go here to here, here to here. So there, this one, it cancels out, but the force is just a little bit less than the tension. So you can keep creating these triangles. So it does create this straight.
that's
Yeah,
interesting.
That's
I
kind of
really like that.
Lots of symmetry in physics stuff. All right, so another word you'll see a lot is amplitude. And whether it's talking about a pendulum or a mass on a spring, because those are the, whenever you see simple harmonic motion, it's going to be one of those two things, a pendulum or a mass on a spring. That's your only two examples. So if it's a mass on a spring, it's how far is the mass from equilibrium, either to the right or the left. So the A is not the distance from the left to the right. It's how far is the left from center, or how far is the right from center. It's always how far is it from that equilibrium central point. And they usually do use capital A for that measure, for that amplitude value. It's the maximum displacement. It would be the same for a pendulum. If they used amplitude for a pendulum, how far out, but it's going to be an angle now. So it'll be a theta angle for a pendulum. What's the amplitude out that we pull the pendulum before we let go? So amplitude is another keyword that you're going to see potentially in questions, and that's what they mean by the word amplitude in simple harmonic motion. Now, you've learned amplitude in your math classes, and we're going to see that relationship here in a minute. So let's do a quick review of Hooke's law, because again, if I were a betting person, I would definitely say you're going to see Hooke's law more than once in the exam, probably somewhere in a free response question and probably somewhere in the multiple choice. So let's just do one quick review. We've done Hooke's law multiple times this year, but here's an example, pretty simple, straightforward question. This could be a multiple choice question. If you have an unextended spring that is stretched by a force of 20 newtons that causes it to stretch 0.4 meters, and then you instead push that same spring with 16 newtons of force, how much would it compress? That's the question. And this would be straightforward enough. I could see it being a multiple choice. But you do have to do a couple of steps thinking this through. What is going to be the same in both scenarios?
The spring constant?
The spring constant, yeah. It's the same spring. So what is Hooke's law? F equals kx. So the force is not constant. Once it's 20 and once it's 16. The displacement, the compression or extension will not be the same. a greater force is going to stretch it a longer distance. So a lesser force is going to compress it a lesser distance. So our answer should be less than 0.4. But what we don't know yet is the spring constant, and that's the one thing that stays constant, hence the name spring constant, right? So we can find the K value using the first scenario, scenario A. We know the force of pull is 20 newtons. We know it gets stretched 0.4 meters. So the spring constant is 50 newtons per meter. Now, in scenario B, the spring constant is not going to change. It's constant. So we've got a K value now of 50 newtons per meter. And now we're only pushing with 16 newtons of force. So if we know how much force we're applying and what the K value is, we can figure out, oh, it would only compress 0.32 meters. So this would be an example of a multiple choice kind of Hooke's law question. And almost every year there's some kind of Hooke's law in the multiple choice. Questions about that one? Making sense? Hooke's law is on here, down here, third one from the bottom, right above the energy of a spring, the potential energy of a spring, elastic potential. They're right there together. All right. So we know that the length of the spring here never mattered. That we didn't need that at all to answer this question. Now, what does simple harmonic motion mean more with a mathematical definition? Well, mathematically, because one, it's a restoring force, and two, it's a variable force. What we know about simple harmonic motion in both springs and pendulums is that there is a relationship between the acceleration that the object experiences and how much it is displaced from its equilibrium position. So like we looked at before, if we displace it a lot, that takes a lot of force, which means it's going to have a large acceleration. If we displace it a little, it's going to have less force required to do that. Therefore, it's going to have less acceleration. If we don't displace it at all, it has no acceleration. Right? So that's what we can think about. That's the relationship. For simple harmonic motion to be true, we know that the acceleration that the object experiences has to be directly proportional to how much we displaced it. The more we displace it, the greater the acceleration. Because the more we displace it, the more force that would require. Make sense? Any questions about that relationship? All right, so then how does this help us prove that certain things are actually simple harmonic in nature? We know we come back to, it seems like everything we do this semester, we always come back to Newton's second law one way or another, right? Must be an important deal. So we know for a spring that Newton's second law still applies, and the force that a spring applies is K times X. It's a restoring force. That's all the negative really means. So if we isolate the alpha, or it's not the alpha, the A, the acceleration, we get the spring constant over mass times the displacement. And we know that the spring constant is constant, and we know that the mass is constant. So basically this equation, A equals K over M times X, is A equals a constant times X. Therefore, it does follow this relationship and proves why mathematically those mass on a spring scenarios are actually simple harmonic motion. Their accelerations will be directly proportional to the displacements. All right, so now you'll notice here it says, therefore an object oscillating on the end of a spring, and then in parentheses it says that obeys Hooke's law. So again, they'll often say that. In fact, usually they wouldn't say that obeys Hooke's law. They'll usually say an ideal spring. And when they say ideal spring, that's all they're meaning is it obeys Hooke's law. You can use F equals KX. And again, I've not seen them ever give you an example where it isn't obeying Hooke's law, but just I want to make sure you know that when they use the word ideal, that's what they're meaning. All right, now let's look at circular motion again real quick, going back a few units. Period and frequency, because period and frequency are going to be used the same way for simple harmonic motion. Period is how much time it takes in seconds for one oscillation or one cycle. So with circular motion, we talked about it being a cycle. How long did it take to go all the way around one revolution? So for this first example, it has a period of 2 seconds. And then we know frequency is how many oscillations happen in 1 second. So what's the frequency of that first example? How many oscillations does it go through in 1 second?
0.5.
Half of one, right? It goes halfway in 1 second. Make sense?
Yes.
All right. Now that's going to be the same. You'll notice here we're looking at uniform circular motion, but in the definition they say oscillation. So what they're saying here is you learned this with uniform circular motion. It's the same thing for an oscillation, but instead of going in a circle, it's just how long does it take the pendulum to go all the way over and all the way back? For a spring, how long does it take for it to go all the way over and all the way back? That it means the same thing.
And there's
Okay.
a problem like that on the springs and oscillations, positive physics.
What's that?
There's a problem like that on the springs and oscillation, positive physics.
Oh,
And
like
it made
this
you
one?
go on like a I'm forgetting what it's called, but that website
Mhm.
that like does the demonstrations.
Uh-huh. So if we speed this up a little bit, let's make the period 1 second. So it only takes 1 second to make the revolution. What's the frequency?
1.
Yeah, 1 hertz makes 1 cycle in a second. If we speed it up again, and now the period is half a second. Frequency is
2.
2, it makes 2 cycles every second. And then if we speed it up again, and
And
the period is a quarter of a second, the frequency is
4.
4.
Oh, 4.
So remember, remember frequency and period are just reciprocal. Just like it was with uniform circular motion, same relationship now. Even though now we're talking about oscillations instead of revolutions, same relationship. Defined basically the same way,
It's 2
both
times.
reciprocal, use the same units, use the same variables.
Can
Yeah,
I go back one Saturday?
this one?
Yeah, thank you.
Does that little alpha looking thing mean, A is directly proportional to negative X?
Yeah.
I think.
Is it alpha or is it just a fancy symbol?
I don't think it's alpha, I think it's a fancy symbol.
It's a fish.
It's an infinity that got sliced.
Yeah, can you?
Yeah.
All right. All right, so this equation is how you can find the period of a spring that's moving in simple harmonic motion. And it is, you can see the relationship to circular motion. We got a 2 pi there. Okay, so it must be somehow connected to circular motion. And you can see it's based purely on the mass and the spring constant. It doesn't matter what the length of the spring is. It doesn't matter what the value of G is. It doesn't matter how far we stretch it or compress it, as long as we don't break Hooke's law. So as long as we don't stretch it so far that it damages the spring, or as long as we don't compress it so far that it damages the spring. If it's an ideal spring and it hasn't been damaged, it'll follow Hooke's law. And if that's true, then this equation is one that you can use to solve the period. And this equation is given. So when we learned period before, we saw it's right here. T equals 2 pi over omega. 2 times pi is the circular relationship, omega is the angular velocity. And then it also says T is equal to 1 over F. So that's what we learned back in the uniform circular motion at the beginning of this semester. Right underneath it, TS, period of a spring, 2 pi times the square root of M over K, just like this. The only thing that's different is instead of the whole word spring, it's just a letter S. Right there for you. And then right underneath it says T of subscript P. What do you think the P is for?
Pendulum.
Pendulum. So period of a spring, period of a pendulum. All right, they're right there. And they're straightforward, just mathematical equations that you don't need to memorize. You just need to know, hey, go to the formula, use the formula. If it's a spring, use the S. If it's a pendulum, use the P. All right. Now, I don't usually do a spring lab where we actually find this period, but I do usually do one with the pendulum. And we might take some time to do that after we're done with our exam, but I want to make sure you're well prepared for the exam first. So I don't think we'll do that demonstration, but we can prove both of these actually. All right. Now this we've already talked about, but a quick reminder, the potential energy of a spring is 1/2 kx squared. And we actually went through this whole process before of graphing the force times the displacement, proving that the area underneath it would be the work done, and it's equal to the 1/2 kx squared. And since work is energy is the ability to do work, this amount of work done is the energy that's stored in the spring. So This is the equation. We already knew that from before. It's right down here underneath Hooke's law. Just a quick reminder, don't forget that equation if you need to know the potential energy of a spring. Again, it only applies to ideal springs. Again, only saying that to make sure you don't forget, whenever you see the word ideal spring, that should be your clue. Use Hooke's law. Anytime you see that phrase, it doesn't mean anything else special, just use Hooke's law. Now, energy is conserved if we talk about the total mechanical. So right here in this picture, we see initially it is fully compressed and then it pushes the object to equilibrium, but because then it has momentum, it goes beyond equilibrium and stretches out the other side. Once it can't stretch anymore, it pulls it back to equilibrium, but because it has momentum, it doesn't stop at equilibrium, it keeps going. And because there's no external forces here, we see that it just keeps oscillating back and forth between having all spring potential energy at the amplitudes, the far edges, and having all kinetic energy at the equilibrium position. But the total mechanical, the blue part, stays constant. And understanding this connection that all the way to the amplitude on the left, that's where it has zero velocity because it stops for an instant. And therefore, zero velocity means no kinetic energy. All the way to the right, it stops for an instant. No velocity, no kinetic energy. Therefore, all potential energy. Right? In the middle, the spring is relaxed. It's not pushing or pulling. If it's not pushing or pulling, there is no net force. If there's no net force, there's no acceleration, right? And so at that point, that is maximum velocity and therefore maximum kinetic energy. All right. So just a review. We've kind of talked about this before, but just want to review that again. Now, this is a more of a connection to waves and also a little bit to your math in terms of amplitude. So I just want you to see here that if we think about these as waves, which is no longer on the AP exam, it moved to AP2. Well, it was already in AP2, but it used to be in both. And then they just decided there's no reason to have it in both anymore. So they took waves out this year. But this kind of shows you that we could graph this kinetic energy flow as a wave and the potential energy flow as a wave. And where the crest of kinetic energy is the highest, that's when the potential energy is the lowest, 0. But if you add their values together, they always add up to the same value.
Whoa.
Okay, I'm going to show you a better scenario of this in a couple slides here, but this is just one way to look at it. All right, the last equation, again, it's on here. I already talked about it. The period of a pendulum, it's right underneath the period of a spring. Instead of the whole word pendulum, it just has the letter P, but otherwise it's the same. And you can see again the connection to that circular motion, that 2 pi, because of that rhythmic pattern of simple harmonic motion. And then instead of m over k, it's L over g, where L is the length of the pendulum and g is the acceleration due to gravity. So if we're on Earth and relatively close to the surface of the Earth, g is just going to be 9.8 or 10. The only reason it would change is if we went like to a very high elevation, like top of Mount Everest, or took it to another planet or the space station or something like that. Otherwise, the g is just a constant. You'll notice, though, that mass doesn't matter. If it has more mass, that generates more torque. If it has more torque, it's going to have greater acceleration, angular acceleration, right? So why doesn't it change the period? Well, if I have more mass, it's going to accelerate faster, but it's going to also have more inertia. It's going to be harder to accelerate because of its inertia, right? Because remember, torque is I times alpha. So the greater m gives it more alpha, but then the I is greater, or sorry, less alpha because the I is greater, because there's more mass. So we have the mass canceling out. It doesn't matter. And how far we pull it to the sides also doesn't matter, because if I pull it further to the side, it's going to accelerate more and be able to reach the bottom in the same amount of time, because gravity is the one thing that's pulling it down. Now, one thing you should know in case they ask you a question about a lab-based pendulum scenario, the angle, if you go about 30 degrees or more, it starts to break down. We don't have time, there's only a couple minutes left. We don't have time really to talk about why, but part of that is because of the tension in the string changing as we start bringing it further out. But that's one thing. If they give you a pendulum question that's more experiment based and they ask, how could you improve it? One thing you might want to look for is just that the angles are 30 degrees or less. So just kind of keep that tucked in the back of your brain as well. That, again, it's very rare, but if you have a pendulum question that's about an experiment, you don't want to use large angles. You want to use small angles like 30, 25, 20, 15, 10. You don't want to go above 30. All right.
So for an ideal pendulum, it wouldn't matter, but for a real pendulum, it's better to stay small.
Yes.
Okay.
Yeah. So if they give you a procedure and ask you to make improvements, if the group was like going up to 60 or whatever, you can just say, this equation for period of a pendulum really only applies at smaller angles, so they should reduce the angles of their trials. Again, I highly doubt you're going to see that, but I'm just trying to think of everything I can imagine them asking and trying to throw those out at you to think about. All right, now here is just the last little bit, how it connects to circular motion. You can see this object is moving in circular motion. And you can see on the right, it's tracking its vertical position, which generates a very simple harmonic pattern, a sine wave. And that also connects to waves, which again, we no longer have, but I want you to see all these overlapping concepts. Circular motion, simple harmonic motion, and waves are all very tightly intertwined. And here's your chapter 12 summary to wrap it up. We've known Hooke's law for quite some time. We've known spring energy for several weeks now. We knew that frequency and period are reciprocal for quite some time. Today, we just talked about the fact that simple harmonic motion just means the acceleration is going to be directly proportional to the displacement. And now we've got our last two equations of the year, which are both provided. You don't have to memorize them.
Let's go.
Epic.
All right. So I think we're out of time. So let's, for Rocky, Sally, Kyle, if you guys have any questions for me, feel free to stick around. But if not, you guys are free to go, and we'll see you Wednesday. Hope you have a good day.
Thank you.
And for you guys that here, we'll just do our normal cleanup routine, and then you guys can head out to lunch as soon as we're done with that.
Epic.
Probably should see it, right?
Yes.
Jackie was here beside you right there.
Yeah.
Alrighty. Thank you.
Yeah, have a great day.
Thank you.
Enjoy your lunch.
Thank you, Mr.
See you. You're welcome. Thank you, sir. See you tomorrow. All right, see ya.
Thank you.
You're welcome.
Thank you.
You're welcome, Aiden. Good to see you again.
Yep, you too. Do we have advisory this week?
Yeah, I think we do.
Okay.
Wednesday. Yep. Okay.
Thank you.
You're welcome.
Thank
Bye.
you.
Bye, Nat.